and equilibrium. We almost never feel only one force at a time. Friction and weight are two forces that might act on you at the same time. To figure out how or if things move, we need to add up all the forces that are acting on them. This section is about how forces add up. The sum of all the forces on an object is called the net force. The word net means total. Net force also means the direction of the forces has been taken into account. Consider a flying airplane, figure 414. Four forces acting on the plane: weight, drag, air friction, the thrust of the engines, and the lift force caused by the flow of air over the wings. For a plane to fly at a constant speed in a level path, the forces must all balance. Balanced forces result in a net force of zero. A pilot must always be aware of these four forces and know how to change them in order to speed up, slow down, lift off, and land. For example, to speed up there must be a net force in the forward direction. The thrust must be greater than the drag. To climb there must be an upward net force. The lift force must be greater than the weight. To calculate the net force of an object, you must add the forces in each direction separately. Remember to define positive and negative directions for both the x direction and the y direction. In the diagram above, the plus x is to the right and the plus y is up. The net force in the x direction is zero because 20,000 newtons and negative 20,000 newtons add up to zero. The net force to the y direction is plus 55 newtons, plus 55,000 newtons, minus 50,000 newtons. The plane climbs because there is a positive upward net force. Two things can be true when many forces act on the same object. One or the other is always true, figure 415. 1. The net force is zero, or 2. The net force is not zero. When the net force is zero, an object at rest will stay at rest. When the net force is zero, we may say an object is at equilibrium. Equilibrium does not mean there are no forces. Equilibrium means all the forces cancel each other out, leaving zero net force. The idea of equilibrium is often used in reverse. Instead of thinking an object is in equilibrium stays at rest, we think an object at rest must be in equilibrium. If an object is at rest, the net force on it must be zero. This fact often allows us to find the strength and direction of forces that must be there even if we don't directly cause them. If the net force is not zero, then the motion of an object will change. An object at rest will start moving. An object that is moving will change its velocity. In Chapter 5, we will learn about how unbalanced forces cause acceleration. Forces. Imagine a book sitting on a table, figure 416. Gravity pulls the book downward with the force of the book's weight. The book is at rest, so the table exerts an upward force on the book called the normal force. The word normal here has a different meaning from what you might expect. In mathematics, normal means perpendicular. The force that the table exerts is perpendicular to the table's surface. The normal force is also sometimes called the support force. A normal force is created whenever an object is in contact with a surface. The normal force has equal strength to the force pressing the object into the surface, which is often the object's weight. The normal force has opposite direction to the force pressing the object into the surface. For example, the weight of the book pressing down on the table surface. The normal force is equal to strength to the book's weight, but acts upward on the book in the opposite direction from the weight. The normal force acts on the object pressing into the surface. This means, in this example, the normal force acts on the book. The normal force is created by the book acting on the table. What happens to the normal force if you put a brick on top of the book? The brick makes the book press harder into the table. The book does not move, so the normal force must be the same strength as the total weight of the book and the brick, figure 417. The normal force increases to keep the book in balance. How does the table know how much normal force to apply? The answer is that normal force is very similar to the force exerted by a spring. When a book sits on a table, it squeezes the atoms in the table together by a tiny amount. The atoms resist the squeezing and try to return the table to its natural thickness. The greater the table is compressed, the larger the normal force it creates. The matter in the table acts like a bunch of very stiff springs. You don't see the table compressed because the amount of compression is very small. Diagram. How can you keep track of many forces with different directions? The answer is to draw a free body diagram. A free body diagram contains only a single object, like a book or a table. All connections or supports are taken away and replaced by the forces they exert on the object. An accurate free body diagram includes every force acting on an object, including weight, friction, and normal forces. As an example of a free body diagram, consider a stack of books weighing 30 newtons resting on a table that weighs 200 newtons. The books are on one corner of the table so that their entire weight is supported by one table leg. Figure 418 shows a free body diagrams of the forces acting on the table. Because the table is in equilibrium, the net force on it must be zero, the weight of the books acting on the table making the 30 Newton force. The weight of the table acts on the floor at every point where the table touches the floor, each leg. A normal force is created. The correct free body diagram shows 6 forces. The normal force of each of the 3 legs is 1/4 of the weight of the table, 50 newtons. The leg beneath the books also supports the weight of the books, 50 newtons plus 30 newtons equals 80 newtons. By separating an object from its physical connections, a free body diagram helps you identify all forces and where they act. A normal force is usually present at any point an object is in contact with another object or surface. Forces due to weight may be assumed to act directly on an object, often at its center. There are 2 ways to handle positive and negative directions in a free body diagram. One way is to make all upward forces positive and all downward forces negative. The second way is to draw all the forces in the direction you believe they act on the object. When you solve the problem, if you have chosen correctly, all the values for each force are positive. If one comes out negative, it means the force points in the opposite direction from what you guessed. Equilibrium problems. For an object to be in equilibrium, all the forces acting on the object must add up to 0. Figure 419. The net force in each direction must be 0. That means the total force in the horizontal x direction must be 0, and total force in the vertical y direction also must be 0. You cannot mix forces in the horizontal direction with forces in the vertical direction. If you are trying to find an unknown force on an object in equilibrium, the first step is always to draw a free body diagram. Then use the fact that the net force is 0 to find the unknown force. To be in equilibrium, forces must balance both horizontally and vertically. Forces to the right must balance to the forces to the left, and upward forces must balance downward forces. Take a moment to answer these questions.